You know, you can stomp around all day and think something converges, but somehow you have to show that it really has a limit. Very often in analysis, folks, it says a limit exists, and they ask you to find it based on other properties, but at least you know it exists. Then you can do stuff. You can write down lambda, that's the limit, and do some algebra. Here, you don't really know that the limit exists. This thing could go out and oscillate, or go out for a while, look like it's converging, then go to hell somehow. But no, it doesn't do that because it's quotient. The hell. Oh, sorry. Go to hell. Right. I had it upside down. Yeah, I know. Very good. Very good. Very good. So our, I don't know what to call this lemma, is the mutual closeness lemma of partitions that are sufficiently small. That's what allows us to conclude that the sequence of particular partitions here induce Cauchy sums that constitute a Cauchy sequence. And since all the Cauchy sums are real numbers, a Cauchy sequence of real numbers converges to some limit, and that, friends, is the Cauchy integral. Right? And it doesn't, I think there's an exercise or suggested exercise at Berg that says, show that it doesn't matter about the partition. We just did. Once you get sufficiently small, you're going to be close to one of, this is a very special sequence of partitions. But any other partition that gets sufficiently small is going to be real close to one of these, right? And then it will fall into this same Cauchy regime here, and it will not be more than 2 epsilon times b minus a away from one of these, right? So that's what it means to converge. You pick an epsilon. And once the partition gets sufficiently small, it's real close to the special partitions, the binary partitions. But the binary partitions induce the limit. So your arbitrary partition is going to be real close to that limit, right? Well, what's that mean? That then converges. You know, any partition. What's the definition? This means that if the partition gets below a particular value, this sum is within epsilon of the limit. We have arranged that. Yeah, we have done that. So there's the Cauchy integral defined. And we've proved that the Cauchy integral exists for a continuous function on a closed integral AB. Now let's talk about some properties of the Cauchy integral. What happens if you have a jump discontinuity, 1, somewhere in the middle of the interval of integration? Is it still integrable? What do you do? Stop and start, right? You do that? What do you do? You stop and start twice, right? Bert asked these questions. How bad can the function be? How naughty can the function be from being continuous and still have the Cauchy integral? So we've decided that a finite number of jump discontinuities, we just stop and start at the jump discontinuity. Because between any 2 jump discontinuities, it's continuous. That begs this question. Here's a little fine point. This is what analysts worry about. Suppose the function is tooling along and it's open there, closed there, and it gets the feed. What exactly, how do we define the integral to this point here, the intermediate point C? I can see SEE that the function is left continuous from the right here, continuous from the left here. So the Cauchy integral on that integral CB is fine. But look, we've got an open point there. How can we define our way around that?
You get a finite partition, so you're with epsilon C.
Yes.
On the right end of that interval.
Okay. It's
bounded.
It's not continuous on AC.
No, it's bounded. So
Bounded doesn't mean uniform and continuous. Like that. Bounded doesn't mean uniform and continuous. So what can we do? We extend the function by continuity. We say, all right, I would like, I split this thing into two complete different integers. So I consider the interval A, C, extend this piece of the function, take the limit as it gets to C, right? Do the Cauchy integral there. Put that aside. Now consider the integral using this value at C and go to B, right? So I'm going to use two different values at C. But then if I close this thing off and extend the function, it's uniformly continuous again, and the Cauchy integral exists. If I don't do that, I'm violating my note to self here from a second ago that said the Cauchy integral only likes to be fed continuous functions, right? Because you need uniform continuity to control the epsilon to go through the whole schmear. So as it sits, I can't handle that without massaging this thing a little bit. I artificially extend the function to that point, do this integral, put that aside, forget it, and do this integral using this value f of c. Right? So I can clearly do that a finite number of times, and I can stop and start it. So we can have a Cauchy integral of a function on a closed interval with a finite number of jump discontinuities. Can I have, I think they call them discontinuities of the second kind, like close encounters of the third kind. What if the function has an asymptote and it becomes unbounded? Can't do that, can I? When does it ever exist if it becomes unbounded? You know, Dave, some authors consider plus and minus infinity to be perfectly good limits. So they operate in the extended real number system, and then there is, well, it's unbounded, but it's never undefined. Defined, but unbounded. Just, I don't know what it called it. So infinities cause us to hiccup. Here's, yes sir, I'm sorry.
You said a finite number of jump discontinuities. Would a finite number of removable discontinuities be the same thing?
Well, with a removable discontinuity, why don't we just remove them all? And then you have a continuous function. You could even have try to actually formulate them here. I guess you could have.
I'm just thinking of like a line or something with which is open in circles.
What if you had this infinite product? And what the hell's the graph of that? Oh, it looks like one with a lot of shotgun shell holes in there. What's that look like when k is 1? K is 1. 1, I have to strike 1. Sorry. If x is 1, then when k is 1, it's undefined. When k is 2, and x is 1/2, it's undefined. When k is 3 and x is 1/3. So it has a lot of points where it's not defined, like countably many places where it's not defined. But I think they're all removable. In every one of these, we just define the function that we want.
So we could have had an infinite number.
I think we have, for this function here, it has countably infinitely many removable discontinuities between 0 and 1.
And it's still be closer.
I think it will. I think the criteria is that the set of discontinuities has to have measured 0. Lebesgue measured 0. In other words, the bad behavior of the function has to be confined to a set whose total length is arbitrarily small.